In the last video, I talked about this rule of thumb which we can use to tell whether a solid is a conductor or an insulator. This rule being that if a solid is an insulator if all the occupied bands are full. Now it's not something which is easy to understand in a simple way. If the bands are occupied, it means that all the energy levels in a particular band is full. Like in the case of helium, in the first band, they're all full and the other bands are empty. Now it doesn't mean that the electrons cannot move. It does not even mean that electrons cannot move from one atom to another. There's always a chance they can tunnel through. And what it means is that for some reason, the wave nature of the electrons interact with the periodic, meaning the periodic arrangement, the regular arrangement of the atoms. Right? The wave nature of the electrons interact with the regular arrangement of the atoms in such a way that even though the electrons can move, right, it has a net effect of giving a zero current if you try to apply an electric field, or if you try to connect a battery to it. So for this topic, that is all I will say about this. The full reason is deep and complicated, so I won't go into it at this level. So let me then maybe complete this statement by saying that let's see. Okay, let me just kind of complete this statement by adding that solid is an insulator and it is a conductor if an occupied band is not full, or sometimes it's described as if it has a band that is not fully occupied. Right, you can express this in different ways. Okay, so that's that. Now let me now redraw this picture in a way that is simpler, that is more commonly shown. Okay, having to draw all these potentials and lots of energy levels for each atom is a bit troublesome. So before I delete this, let me just emphasize again that I seem to have drawn these bands of lots of levels for each atom, for each atom separately. Now it doesn't mean that each of these bands belongs to the atom itself. Okay, previously, when the atoms are separate or when they are far apart, each of the energy level in the atom belongs to itself. That is kind of more or less correct, right? If the atoms are very far apart. But when they are close together, like touching each other in a solid, if touching means anything, now that we know about atoms, when the atoms are very close by, the wave property of the electron, the fact that it can spread out over to other atoms, means that the energy levels become of all of the atoms become changed, right? So that we have this band structure. So these lines that I draw for each band over each atom refers to energy levels for all of the atoms at the same time. So this picture here, these bands here, is for all the atoms. So these are really not separate, right? They refer to the same bands, right? Because the single atom itself would just be this, right? So this is a combined effect of all the atoms, and it belongs to all atoms. So therefore, I don't have to actually draw separate atoms and separate bands. All I need is to just to draw one of them. I just need to draw one of them. And usually, when we try to understand, or in questions where we have to talk about conductors, insulators, and semiconductors, we would usually only need to worry about two bands. The highest band that is occupied, and the next band that is not occupied. So like when I was talking about lithium just now, lithium atom in the last video, I talked about an occupied band and a not fully occupied band. So usually we just need to talk about maybe a fully occupied band and a partly occupied band, or for the helium atom, a fully occupied band and an unoccupied band. Okay, so let me just simplify this drawing now. I can remove the whole lot, perhaps. Yeah, I think so. Okay. So let me try and draw this. Now for the band, instead of drawing lots and lots of lines, I'm just going to draw a box, and this area represents lots and lots of lines for one band, and another area here perhaps. Could mean another band with lots and lots of energy levels inside. So what is often shown is that right, let's say I have a band which is fully occupied. I show it by shading this, so it's fully occupied. And then a band that I don't shade, or I use a different color to represent that is unoccupied. So this is how it might be drawn schematically. So we might, if you think about this as a fully occupied band, and think about this as an unoccupied band, then what we have here is an insulator. Okay, this is the next band up, and it's unoccupied. That's fully occupied. So all the occupied bands are fully occupied. So this is an insulator, right? So that's what this is. Then we have the other case, the other possibility, okay, in which you might have, say, a band. Again, let me draw two bands here. Maybe this is fully occupied, and this band here is partially occupied. So this is not full. a band here that is not full, and that is again full. So what I have here then is a band that is not full, and if I have a band that is not full, it's a conductor. Now there is another way in which this is sometimes drawn, and that is where they are drawn as overlapping bands. One band here, maybe another band here. Okay, so that's also possible, where we have let's shade this. Okay, so the electrons that fill up to here, in effect, fills up the lower band fully, and at the same time, fill up. There are enough electrons to fill up both the lower band fully, and as well as the upper band, which happens to overlap with it. So in that sense, the upper band is not full. Okay, it's not full. Upper band is not full, but the lower band is full. So that's another configuration, another possible arrangement that can happen in a solid. Right? Band structures are really complicated things. So I just show both picture as possibilities, and both can be conductors. Right. So while we are here, let me write down some terms. Now, so we are sort of looking at, say, if you imagine, that these bands are made of energy levels, and then there would also be energy levels below it. There might be bands below this which I have not shown, and likewise there would be bands above the unoccupied bands. And there will be, in fact, that I do not show. So we are really looking at this, if you like, the boundary between filled and unoccupied, and between occupied and unoccupied bands or levels. Even here, all right, even here we are looking at this boundary here, where below this boundary is occupied, above is not occupied. So we are looking at this boundary between occupied and unoccupied. Now, for this lower band, okay, for the lower band of this boundary, we call it the valence band. That is the word used to refer to the band below that if you like, the boundary of occupied electrons, occupied levels, and the band above is called the conduction band, and you would use it, for all of these cases. All right, so in this case, you would say the conduction band overlaps with the valence band. In this case, you would say the conduction band is empty. In this case, you might say that the conduction band is partially filled. Okay. Okay, so as an example, maybe think of an example for, say, an insulator. It could be, say, some plastic, just for example, some kind of plastic. Or if I prefer to talk about elements, maybe say, I don't know, like nitrogen. But nitrogen is a gas. It can be frozen solid, right? Let me just think of a solid example like phosphorus. Okay, so this might be phosphorus, for example. So conduction band, for example, this might be copper or say lithium, right? The example that I looked at just now, lithium. And yeah, so that can conduct electricity. This one cannot. Now, as my next example, maybe the last one for this video, I want to look at something in between the two, between an insulator and a conductor. So what can be between an insulator and a conductor, you might wonder? Well, you might have guessed it, a semiconductor. Now this is a very, if you're looking at this, you probably heard of semiconductors all the time these days, right? But even so, if you think in terms of all these ideas about insulator and conductor, I mean, how can something be semiconducting? Surely it either conducts or not, right? So let's try and understand this. Now what I'm drawing here is not so different from what I had drawn for an insulator. I'm going to draw the lower band shaded, meaning that this is fully occupied. And upper band, the conduction band, is unoccupied. So in principle, according to the rule of thumb that I described so far, that should be an insulator, right? That should be an insulator. The only difference between this drawing and this drawing is that those two bands are closer together. But surely, according to the rule, it should be an insulator, right? Right. Yes, except that, you know, in physics as in life, right, things can always get complicated. Now in this case, the complication is this. You see, there are electrons here at this level, and there are no electrons there in that band. But if the two levels are quite close, then, you know, when there's temperature or when it is warm, the electrons can gain thermal energy, and thermal energy can come from the vibration of the atoms colliding with each other, and this motion of the atoms, they would move more and more. There would be more and more thermal energy as the temperature goes up. Right? And even typically at room temperature, the atoms will be vibrating and moving. So there will be energy that disturbs the electrons. Now, if there's enough energy from this thermal energy to overcome this energy difference, right? This difference in energy. If this difference in energy is roughly, you know, the kind of magnitude of the thermal energy, then it is possible for an electron at the lower band to gain enough thermal energy to jump up, for some of them to jump up to the conduction band. So the effect of this is that we could get some electrons because of thermal energy. So this is an important point of the semiconductor behavior. In a semiconductor, the bands are close enough, right? The two bands, the conduction and valence bands are close enough that thermal energies can excite. I'm using rather technical terms here. Excite just means give energy to the electrons. Can excite electrons, right, from valence to conduction band. Okay, so this sentence might be a little bit abstract, particularly about this thermal energy. Now, exactly how much is this thermal energy? For example, where I've talked about where it can come from. It can come from the motion of the atoms, because as long as you're not at 0 Kelvin, the atoms can have some movements. And if things get hotter, the atoms move more. So that's how I have described it when in the videos on thermal physics. And for example, at room temperature, we would expect the thermal energies usually to be about, maybe I'll just write out a number here. At this thermal energy at room temperature is about 1/40 electron volts. So if it helps to make things a little bit more direct, okay, but there's no need to remember this number. So this effect of the thermal energy or of the temperature means that because some electrons can get excited up to the conduction band, the semiconductor can become conducting. And the higher the temperature is, the more conducting it becomes. In other words, the resistance drops with temperature. Now, you might have remembered me talking about this when I talked about thermistor in the topics on electrical resistance. Now, there is a lot more to the properties of semiconductors that will make it very useful. I shall talk about this in the next video.